Atoms form bonds to lower the energy in their system. Bonding allows both atoms to become more stable. Chemical bonds are typically formed to fulfill a total of 8 valence shell electrons. Atoms with a set of 8 electrons are usually more stable because their valence p sublevel is filled immediately before starting the s sublevel of a new energy level. There are different types of chemical bonding. Ionic bonding has different atoms transfer electrons to form a cation and anion. The opposing charges of these particles draw them to each other to form ionic compounds. Covalent bonding involves the sharing of electrons to complete each atom's octets and form molecular compounds. Metallic bonding has ions held together by a field of electrons and results in metallic compounds. To determine between ionic and covalent bonding, we have to look at the difference in ionization according to the Pauling scale. Ionic bonding occurs between elements, usually between a metal and nonmetal, with an electronegativity difference greater than 1.7. Of course, the atom with the greater ionization energy will be the anion in the molecule. Covalent bonding occurs typically between two nonmetals. Covalent bonding with an electronegativity difference greater than 0.4 up to 1.7 is considered polar covalent bonding, where there is an unequal sharing of the electrons. Essentially, one atom may have the shared electrons more than the other, resulting in a polar bond. In metallic bonding, valence electrons freely move around the positively charged nuclei. Metals are malleable and conduct heat and electricity well because of this. Atoms can be visually represented using the Lewis dot diagram, where the elemental symbol of an element represents the nucleus and the surrounding dots represent the valence electron shell. Each side of the kernel represents an orbital, which holds 2 electrons. In ionic compounds, oxidation numbers will predict the types of ions an element will form to become more stable, based on the Octet Rule. Sodium has a positive 1 oxidation number because it is likely to give up an electron and have a positive charge in order to become stable. Chlorine has a negative 1 oxidation number because it needs 1 electron to complete its shell, making it an anion. We would write the Lewis dot diagrams next to each other with their respective charges, separated by brackets. For magnesium chloride, notice the order in which we write the Lewis dot diagram. Both atoms of chlorine are attracted to the 2 respective electrons of the magnesium, not to each other. In covalent bonding, the atoms in the Lewis dot diagram fit together like a puzzle because they share electrons. Let's look at water. Oxygen has 6 valence electrons, and both hydrogens have 1 electron each. There are 2 unpaired electrons in oxygen, which serve as bonding sites for the hydrogens. Bonding sites, of course, are places where unpaired valence electrons can come together. The oxygen now has 8 electrons around it, and the hydrogens have 2, which is fine, since hydrogen doesn't obey the Octet Rule. Hydrogen only needs 2 electrons to be stable, as 2 electrons is enough to complete the s orbital and complete the first energy level. Other exceptions include beryllium, which is stable with 4 valence electrons, boron, with 6 electrons, and phosphorus, with 10 valence electrons. Most covalent bonds involve single bonds, double bonds, and triple bonds. These bonds are represented on the Lewis dot diagram by lines. An orbital of 2 electrons not involved in bonds is known as a lone pair. To write Lewis structures, make sure that you start with the atom with the highest number of bonding sites in the center. Then, surround the central atom with other atoms and create bonds with unpaired electrons until there are none left. Finally, make sure that each atom obeys the Octet Rule and be mindful of the exceptions. In methane, carbon has 4 bonding sites while each hydrogen only has 1. Carbon is placed in the center, surrounded by hydrogen and paired with the valence electrons of the hydrogen atoms. This obeys the Octet Rule because each line represents 2 shared electrons, making for 8 valence electrons for the carbon and 2 valence electrons for each hydrogen. Now let's try ozone. Oxygen has 6 valence electrons, and there are 3 oxygen atoms in a molecule of ozone. This leaves you with a total of 18 valence electrons. We start with the 3 oxygen atoms and their valence electrons and begin forming bonds. You'll end up with something looking like this. Ozone is a polar molecule, meaning there exists a dipole moment where the charges are unequally distributed. You'll notice how the molecule isn't symmetrical. Ozone is also a resonance structure because it can be written differently due to this asymmetry. Lewis dot structures are useful because they describe a molecule structure. However, these structural formulas are not realistic because they only show a molecule in 2 dimensions. Similar charges repel each other, so the electrons in a molecule would realistically spread as far apart from each other as possible. Ball and stick models can be used to represent molecules 3-dimensionally. For example, carbon dioxide and water are both molecules that have 3 atoms, yet one is bent while the other is linear. Valence shell electron pair repulsion, or the Vesper Theory, yes, I know it's weird, is a model used to represent these differences in molecular geometry. Valence electrons not used in bonding take up more space than those that are involved in bonding. These lone pairs are what give water molecules a bent shape. Carbon dioxide also contains lone pairs, but due to their positions, it remains a linear shape. To determine molecular shapes, first draw the Lewis structure. We would then look at the ABE, where A represents the central atom, B represents the number of atoms bonded to the central atom, and E represents the number of lone pairs. This is a table that details the geometrical shape of molecules in addition to the angles between their atoms. You're welcome to pause the video now if you want to get a better look at it. Okay, good? Alright. That wraps up this video where we learned about ionic, covalent, and metallic bonds, as well as how we notate some of these bonds and what that means for the overall three-dimensional structure of the molecule. Next time we'll be talking about intermolecular forces, and as always, something link in the description, chemistry videos.